All right. Hello. So I hope things are audible and clear. So if you remember, we spent a little bit of time in understanding how to use linked lists to obtain objects like arrays, binary trees, and so on. And not just diagrammatically, we in fact wrote down the proper formal algorithm for each of those. Right. So now let us formalize another thing that we have seen via diagrams before, which is stacks and queues. Okay, so we have seen stacks and queues before, but now we will do the formal part of it using algorithms. How to insert elements, how to remove elements. We will do those. And before proceeding ahead, I would ask all of you to just go back and revise what we had already done about stacks and queues so that now when I go ahead, it will be easy for you to follow. So I'll straight away jump to the coding part because we have already done the theory part before. Okay, so let me start quickly with stacks. So this is the first thing I want to do here. So a stack, if you remember, a stack is realized by an array of a certain length, okay, of some length uh, n. So let's say let S be a stack realized as an array, right? And then what does it have? It has a top point, right? If you remember, stack has a top pointer, okay, a single pointer, which is the top. All right. So formally, what does it include? So S is equal to pair A comma P, an ordered pair A comma P, okay, where A is an array, all right, and P is just an index. P is an index that takes the value. So let me say P is an index or pointer taking value between what is it 0 and A dot length. Okay, 0 and A dot length. Okay. Further, we'll just use the convention. So we will denote s dot length to be equal to a dot. Okay, so we will interchange when we say s, we will refer to a whenever we are using the array, so that we will really not distinguish between s and a. And p is denoted by s dot top. S dot top. P is equal to the pointer s dot top. It has a certain value. Alright, so S dot length is A dot length and S dot top is equal to P. Set it that way. Okay, so that is the formal part. So what are the things that we need to see? We need to see when a stack is full, when a stack is empty, when can we insert an element, when can we remove an element. Okay, push and pop, if you remember. Those were the operations for stack, or insert or delete. Okay, so let's write down the first thing. So the first algorithm is to check whether a stack is empty or not. Okay. So another convention that we will use is that we will use capital letters to denote the names of algorithms. Okay. Standard convention. Okay. So stack empty S. Okay. What does it do? So now I'm going to write it line by line. Be careful. Okay. So I'll write it inside. I'll use spacing to make sure that we are clear about where we are. Okay. So what is the first command? The first command, just to make sure that we are all in the same page. First command, I'll write start. Okay, so that we all are clear about where things are starting. Okay, and then in the end I will write an end command. It's not required formally, but this is for our own understanding. Okay, so that we are clear about where the algorithm is starting and where the algorithm is ending. So this is the algorithm, the name of the algorithm. This is an input parameter. There is a start and there is an end, and everything else we will write it inside start and end. Okay, right. So what do we want to do now? We want to check whether the stack is empty or not. If it's empty, we want to return true, otherwise we want to return false. Okay. Now a stack is going to be empty exactly when there is no element, right? So the top has to be zero. Okay, not even one. If the top is one, just go back and check. If the top is one, then the stack has one element. So the top has to be zero. So that is the condition. So if s dot top equal to zero, we write equal to because we are using this as a comparison operator. If this is equal to this, compare these two values, and if they are equal, then you do something, right? Single equal to is assignment, right? You assign zero to this pointer. That's not what we're doing. We are comparing. Okay, so there is a distinction. So if s dot top is equal to zero, what do? We return the sense give the output. Okay, what output do we give? The output is true. Okay, this is our text. This is what we will display. Once we do this, what is it? The end, there is an end if, but if it's not the case, then we need to return false. So else, to understand what we mean by else, right? If s dot top is not equal to zero, what to do? So else return false. Is that okay? Once this is done, we are done with the if part. So there is an end if. So okay, so I'll just make a small change. Let's call it start and stop because end comes at other places also. So I'll call this start and stop. Okay, for the algorithms beginning and end. Okay, start and stop. End we will use for other commands. All right. So this was for the stack being empty. The next algorithm is of a similar kind. It's called stack full. Is the stack full or not? Okay. Similar kind actually. So once again, we will start stop, and everything else is going to be inside this. Okay. When is the stack going to be equal to full? When every element in the array, every index in the array has an element, which means the top element is going to be at the rightmost end of the array. Okay. So the rightmost end of the array has the index a dot length or s dot length. Okay. So the top pointer is equal to the length point, the length value. Okay. So that is exactly what we are going to check. If s dot top is equal to s dot length, understand? Which means the pointer is at the rightmost end. Then we return true because the stack is full. If not, else we return false. And this is end. Is that okay? So that was about the stack being full or not full. Okay, space. The next algorithm is about inserting an element into the stack. Okay, which is what we call push. Remember, we have used these notations. So push into the stack S an element A. An element A. Okay, A is the key. If you remember the word key that we have been using, key is the value stored at a particular index. A is the key that we have to insert. Okay? So push s comma a says we have to push the element a into the stack s, the key value a into the stack s at a suitable index. Okay. So once again, our algorithm will be between start and stop. What is the first thing you want to do? You want to check that there are no issues. Okay. So when can you push an element into a stack? You can push an element into a stack whenever you have space. Okay, you want to push one element, there should be space in the stack for at least one element. What does that mean? It means that the stack should not be full. Okay, the stack should not be full. So the stack full algorithm that we just saw before should return false. Then we can push. Otherwise, we cannot push. That's the problem. Okay, so we have to give an error when the stack is full. Okay, so that is the first thing that we have to do. If stack full s, okay, what does this return? So the value that it returns. So we'll check it with true. Right? This is the meaning. When we said here return, it means whatever you write after that is the output of this algorithm. Okay. So now we are checking for the output of this algorithm. Is it equal to this value? Okay, that is the meaning. So if stack full s is equal to true, you cannot insert it. So you cannot insert anything, which means you give an error message. So you give an error message. So let's call this display error. Stack is full. Is that okay? Which means you cannot insert any more element because it is full. Let me just call it error. We don't have to make it too complicated. Okay, so error stack is full, which means this is the error given. Okay. Now if this is not full, else that is when we add the element. Correct. So what happens? Now look at the top pointer. The top pointer of the stack points to the last element in the stack. Now you want to add one more element, right? So the top pointer goes to the right. It increases by 1 when you add this element. Okay, and it has to be added to the next position, right? After increasing the pointer by 1. So else what we do is s top, we first assign it to be one more than the previous value. S top is equal to s top plus 1. What does that mean? Whatever was the current position of the pointer, it's not full, right? This is in the else part, so stack full returns false. So s dot top is not equal to s dot length. It's less than s dot length. So we can always increase it by 1. Okay. So we increase s dot top by 1. And now the new increased value, wherever it points, at that position, we add the value a. So now s dot, so sorry, s at the position s dot top, at the index s dot top, we add the value a. Is that okay? So, okay, one more convention. So, sorry for the confusion. Whenever there is a return statement, I'll always put a semicolon so that we don't have a confusion. Okay? That is full, else, so that we know exactly where the line is stopping. Okay. So now do you see what have we done? We have shifted the pointer to the right by 1. We have an empty space, and there we have inserted the new element. And this is over. This completes Okay, so we have now end. Okay, so this is the algorithm for pushing the element. What about removing the element? That was what was called pop. And if you note, by the structure of the stack, by the property of the stack that we have seen, you can only remove the last element from the stack. Last in the sense wherever the top element, okay, the pointer top, whatever it shows, you can only remove that element. You cannot remove any other element. So we don't have to mention the value that needs to be removed. We just have to say that remove or pop an element. It will remove the element pointed by the top pointer. Okay, one second. So the same thing now. You have start and stop, obviously. That's the first thing that we need to check. If you want to remove an element, there should be an element, correct? Which means the stack has to be non-empty. So that's the first thing to check. So if stack empty s is equal to true, then what do we give? We give an error. Let's say stack is empty. If not, that is when we start working. Else, stack is not empty, so there is some element that has to be popped out. And when the stack is not empty, s dot top is going to be greater than 0. It will be at least 1. So you can always reduce it by 1. Okay? And that is exactly what we do. So s dot top is equal to s dot top minus 1. That's it. We don't really have to, there is no such thing as physically removing the value. The moment you reassign the pointer, the value that was there at the top earlier is forgotten now because the top pointer is pointing to the value before that. So the top has changed already. As we discussed, this is something we discussed even during the lecture. Okay, there's no such thing as erasing an element. You just change the pointer and the value is forgotten. So this is enough. So s dot top is equal to s dot top minus 1. The other thing that we can do is whichever was removed, you can output that value. Okay, so that is the additional thing you do. Return the value. What is the value that we return? So now s dot top, after reassigning, this value now points to the element just before the value that you popped out. Okay, so the value that you popped out is at the index s dot top plus 1. Is that okay? So return the value s dot top, return the value at the index s dot top plus 1. Okay, and then end it. All right, so that completes the pop algorithm. Okay? So what I would like you to do is go back and look at these algorithms: stack.empty, stack.full, push, and pop, uh, on the examples that we saw in the lecture, and convince yourself that this makes sense. Okay, so now the last remark, which is that, see, for each of these, you are basically doing just one step. So you either return a statement, or you return some other statement, or you make a check, right? Or you assign a few values, one, two, or you make two assignments, or you display an error, things like that. You are not really running over a sequence of elements, or your an index variable is not running over a set. Nothing like that is happening. So each of these, if you say that every step takes unit time, there is an upper bound, a uniform upper bound that you can give on each of these. So the runtime is basically order 1. Runtime for each of the above. So let me write this as a remark and just convince yourself. Okay, think about this, convince yourself, and if it's not clear, then we can discuss when we meet next time. Okay, runtime for each of the above algorithms So shall I write it specifically? So let's write it specifically. Stack empty each of stack empty, stack full, pop, sorry, it was push, right? Each of push and pop is big O1. Constant number of steps are enough to run each of these algorithms. Maybe 10 or 20 or whatever it is, but the constant is enough. Okay. So the runtime for each of these is big O1. Okay. So that completes the discussion on stacks. Right. Now let me also go to the second part. Let's consider queue. Alright. Alright, so let me stop this here and let's consider queue in the second part of this video. Okay, so I'll just stop it here and consider queue in the second.